As we wander closer and closer to living a life in the land of science fiction, scientists at UCLA have developed a window that is also a solar collector. Yang, a UCLA professor of materials, science, and engineering, and the director of the Nano Renewable Energy Center at California Nanosystems Institute, joins us to discuss the implications, practicality, and effectiveness. Welcome, Dr. Yang.
Thank you for having me on the program.
It's my understanding that these windows you're developing are 70% transparent. In terms of allowing light in, how does that compare to traditional glass?
Oh, the traditional glass has 90% transmission. However, that's in the perfectly clean condition. So most of the windows, in fact, is about 60-70% transmission.
So if we were able to install these polymer collectors on our houses, we would get about the same amount of natural light than we would most of the time using traditional windows.
That's correct.
Is there a difference in the heat exchange? Would it make the room warmer? Would it make the glass itself or the polymer itself dangerous to touch or clean?
In fact, if everything goes as what I planned, the room will be cooler, not warmer, because our polymer pick up or absorb the infrared light, which is often the major heating source from the sun to heat up the room. So if a building in the summer that often has to turn on the air conditioning stronger to compensate the heat. In that case, the infrared light will be blocked by our transparent solar cell.
So it would actually be beneficial on two levels. One, you would be generating electricity through receiving light, and also because it would be filtering out some heat, you would save energy because you're not using as much.
That's correct.
Sounds wonderful. Now, why are people becoming so excited about the idea of a polymer solar cell versus other types of more traditional solar collectors?
Oh, that's a very good question. In fact, it took us 10 years of research to reach what we currently have. The polymer, or a more popular name is plastic, is in fact the low-cost material can be processed using very simple method. So we can coat the material using spray coating, for example, or a more low-cost web coating process compared to traditional semiconductor like silicon has to be produced using high vacuum and or expensive semiconductor fab. So by itself, we should be able to produce solar panels using printing method that, give you an example, like print the newspaper. I mean, I exaggerate a little bit, but in a similar way that one can print solar panels. So potentially we can have mass production at a much cheaper cost.
Is another advantage to these types of polymer or plastic solar collectors that they're more flexible and therefore less likely to be damaged in need of repair?
That's a very good point, yes. In principle, we can produce them on the flexible substrate, and then they can be mounted in a non-traditional way. For example, the silicon solar panel currently is fairly bulky and heavy, and the installation cost is about 50% of the total cost. So ideally, in our case, that we will be using the plastic substrate, which will enable us to produce a solar panel I call the non-breakable way, which is flexible and can form a different shape.
And in the early application, in the early study of these solar panels, how much power were they able to generate? How much of the total energy picture would this contribute to?
Oh, that's a very good question. Let me give you an example. A typical solar panel on the rooftop, silicon, is about 16%. 18% probably is already high-end. In our laboratory, we produce the transparent solar cell about 4% so far, but we have a plan to reach about 10% efficiency in the next 5 years. In parallel, we have a non-transparent solar cell, which already beyond 10% barriers. So our group is the leading group in this technology as far as breaking a record. So about 6 months ago, we broke the 10% barrier using a tandem, which is a double-layer solar cell, and in that case, it's non-transparent. So we are talking about the efficiency figure is still behind silicon, but we are not too much behind.
Now, would this type of material be more useful for, let's say, office buildings and skyscrapers than it would be for homes, meaning you have much larger planes of polymer being used?
In principle, we could install the solar panels not just on the rooftop, but it could be on the wall, and the area of wall is unlimited, and basically compared to the rooftop, you can. So we should be able to mount solar panels or plastic solar cells, particularly the transparent ones, in the areas which is unlimited to the traditional solar panel.
Oh, so your polymer solar panel is not just designed to be a window, but it can be used anywhere solar powers or anywhere you would want to collect as long as you have a sufficient stable surface.
That's true, including, for example, probably people will think does not make sense to have an indoor solar panel. That, in fact, our solar panel, plastic solar cell has been proved to be more efficient in the low light condition compared to silicon counterversion. That we should be able to have indoor solar panels, or not solar, but to harvest the light during the night that not being used. So those are the new ideas and new concepts that has never been thought before. So I think those are the new possibilities for our technology.
Why do you think that they would be more effective in low light conditions?
Oh, there are a lot of nice, interesting fundamental science involved, and I encourage the young student to study engineering and science to understand that. One possibility, one explanation is when the light is not strong, then we generate less electrons. And in the case compared to a lot of electrons, the electron actually has a term called recombination mechanism, will bring them disappear due to the defects. So in the case of low light condition, we produce less electrons, and the recombination mechanism is not as obvious as you have more electrons. So that's the scenario for now. But we still carry out a lot of nice fundamental research to understand our technology.
Now, in each of our homes on that level, and I may be off base here, we have incandescent, fluorescent, and various other types of light bulbs which produce light, heat, and energy. Is it possible that these collectors would be able to take some of that and turn it into energy as well?
That's true. That's the idea. That is to recycle the photons that are not being used. For example, in airport, let's give an example. You have a lot of high-rise ceilings and then with lighting, and then there are a lot of decorations around the airport to make it beautiful. Our polymer solar cell could be some of the decorations that mount on the wall that, in fact, to take those photons to recycle them and become electricity again.
In practical terms, if I were to get a polymer solar collector window, would I be able to open the window to be able to smell some fresh air?
Oh, absolutely. And my idea is that we will not produce the window. My technology will enable the solar posters, like lamination, like you laminate the 3M Scotch tape to the window. So because, as you mentioned earlier, Andrew, that our solar cell could be flexible if we choose using a plastic substrate. So the ideal scenario would be we will simply have those plastic solar panels that are flexible and transparent, and one can just glue to the window. And the function of a traditional window will not be impacted at all. It would just have a layer of the solar panel, which is hopefully invisible to the light, to the eyes, that and all the functions still there.
Are there any downsides or concerns that you're still wrestling with? You said heat is not one of them. I do know that there were in other solar collectors, there was reflected light, which actually caused burns and things of that sort. Are there any things that you're currently wrestling and trying to solve?
Oh, many things. I never say the heat is not a problem. What I say the heat is that we actually block the infrared light, so reduce the heat to the room. But our solar panel are not yet for commercialization, so we're still working hard to improve the technology from better materials. So we need to work with chemists. And then we need to incur encapsulation to protect the solar cell from being touched. For example, the solar panel should be able to touch one touch a piece of glass. Mm-hmm. And then other issues like since we use a transparent our metal contact, so how to wire those metal contact out. So on the other hand, the system integration are also major challenges. So I think if we are lucky, we can bring the technology to the market in the next 5 years, but it requires a lot of heavy work on it.
Is there any danger of toxicity or exposure to these chemicals or materials?
No, not really. No, those materials are plastic. Let me give an example, like a supermarket plastic bags that one should not worry about the explosive and other things. So those materials, hopefully in the future, should be recyclable. If you're getting old, you just peel it off and then throw it into a recycle bin and can be recycled. So that's the ideal scenario. Again, it takes a lot of work to reach the level.
One of the other questions which almost always comes up when we deal with solar power is storage. I'm assuming that the issue of storage is exactly the same with these polymer collectors as it would be for any other solar collector in terms of things going to the battery life, and how much power you can get both in and out of it.
Well, that's a very good question, and I don't have a solution for the storage better than any others. But my ideal scenario is that if during the day nobody at home or not using electricity as much as one should be, then the electricity can be sold back to the electrical company, the utility company. And then during the evening or night, when people use more electricity, then we can reclaim them from the traditional utility companies. However, for areas is more isolated and that has little connection to the utilities, I think we should deal with the storage that's problem that you just described. And there are batteries can do that. However, that's another technology that I'm not the expert in the battery technology. So that we should use the battery to charge them and during the night to recollect the electricity from the storage devices.
Well, looking through a polymer prism, which allows us to collect energy possibly coming and going, and allows us to see the light. For the Prism on the Voice of Russia, I'm Andrew Hiller, and I was joined by Dr. Young Yang, a UCLA professor of materials science and engineering and the director of the Nano Renewable Energy Center at California Nanosystems Institute. Thank you so much for your time.
Thank you very much.
This look through the prism may be stronger than a locomotive. In this year of the superhero movie, the story of science fiction becomes reality brings to mind Superman squeezing a piece of coal to create a diamond. Scientists haven't quite accomplished that feat. After all, we still are men with feet of clay and not of steel. But what they have done is artificially compress carbon near the hardness of a diamond. To talk about the process and its implications, we are joined by Kanani Lee, an assistant professor of geology and geophysics at Yale University. Now, for years, we've been seeing and hearing a lot about artificial diamonds, decades even. Are these completely different creatures that you're creating?
It's not quite diamond, and actually, we've been able to make we as the larger community have been able to make synthetic diamond for 50 some odd years. by using high pressures and temperatures, and more recently, even with just high temperatures. But this form of carbon that we've made only requires high pressures. And just with high pressures, we can produce a diamond-like substance that is as hard as diamond, or it can damage diamond, which is a measure of how strong material is or how hard a material is. And so it is different. It has a different crystal structure and different how do we say this? A different compressibility than diamond. Not quite as incompressible as we find, but about on par to diamond, which is the hardest material known to people.
Now, in terms of appearance, does it have the same opacity, transparency? Does it look like a diamond, or does it look like squeezed coal? Is it dark?
So it is transparent, like diamond is, but we've only been able to produce very, very tiny grains, so nanocrystalline-sized grains of this new form of carbon that has been called M carbon.
And you told us how it's made. What do we think might be the practical application for this at some point? How do you want to use it?
Well, if we can figure out a way to stabilize this material so that I could actually hold it in my hands. Currently, I need to be able to have it under high pressures for it to be stable. But if I could get this material so I could hold it in my hands, one could conceivably replace any diamond parts, say in industry, where industrial diamonds are used quite frequently, and you could replace your industrial diamonds, potentially even your gem quality diamonds for this M carbon. That's a possibility, and if you could make this in a large scale, you could conceivably do it rather inexpensively, thus negating the need to use to produce synthetic or use natural diamonds.
I was going to
potentially, I say.
Yeah, I was going to ask about expense. At this point, how much does it cost to produce these particles at all?
Let's see. Doesn't really cost much of anything. I mean, as long as you have the equipment available, the carbon itself is dirt cheap. I mean, it's, you could almost think of taking a piece of pencil lead and just compressing that.
Sure, I used to use graphite all the time in art classes.
Exactly. So if you took your graphite pencil and you took a piece of, you broke the tip off, I don't know, however much that costs. As long as you have a way to pressurize it, it doesn't really cost much of anything.
So this really could commercially eventually save millions or hundreds of millions of dollars in various industries.
If we can figure out a way to stabilize it. So there's a number of ongoing experiments trying to figure out a way to stabilize it. Because currently we can produce it at these very high pressures, but once we take those pressures off, it ends up reverting back to your graphite pencil. So it's in this intermediate space of going from this high pressure form into what it would like to be is graphite. It's a very, very small energy barrier. And so we need to figure out a way to tweak it such that it never goes back into the graphite pencil form. And so that's an ongoing set of experiments.
So the graphite acts effectively as a sponge, and when you're pushing the pressure down, it squeezes, and as soon as you release it, it re-expands. How quick is that expansion?
It's actually the compression itself. It's rather slow, and it's the compression itself. In order to take and I'll use your analogy, like a sponge, and then squeeze it down, is actually rather slow. And then the reversion back into the graphite form is also slow, but slow on the sort of minutes to hours. So it's not immediate in a split second, and then it's also not super long, like years or on the time scale of hours. Does it take to revert back? Once it's at and this is still at relatively high pressures. Once it's at ambient conditions, at this point, there's still only just the graphite form.
Let's talk about the graphite itself for a moment. It was my understanding reading the article that it took a long time for you guys to find the right kind of carbon that could be successfully squeezed into this level of hardness. But in the interview, I'm getting the sense that it would work with almost any type of graphite.
Oh, so what took a long time to figure out was the actual structure. So for around about 50 years now, this new form of carbon has known, unfortunately, or it was first observed, but it wasn't actually known what that structure looks like. And so there had been early experiments back in the 60s that tried to figure out what the structure was, but they were unsuccessful. Different groups got different structures, and nothing was reproducible, or very, very, very difficult to actually pin down what the crystal structure was. More recently, with the advent of computational mineral physics and theoretical means, density functional theory is another way to call it. Various groups have been looking for the structure of this high-pressure graphite phase. That's not diamond, that's not graphite, and that is produced just with high pressures. And it was actually so we were able to successfully verify, confirm what this structure was, just with these set of experiments, and it actually ended up matching very well the structure of this monoclinic structure called M-carbon that was first proposed in 2006 by a group that's led by Artem Oganoff, who's now a professor at Stony Brook University in New York.
So in pedestrian terms, it sounds like the trick wasn't figuring out how to squeeze the graphite, the coal, but it was how to squeeze it into the correct shape that matched your projections. And once you figured out how to squeeze it, you were able to produce these very hard pieces of graphite, which almost near the level of diamond. Is it easily repeatable at this point?
The pressurizing of the graphite into this high-pressure form is quite routine. It was the identification of the phase that was difficult. A monoclinic structure has low symmetry, and so the typical way that people identify crystal structures is by using X-ray diffraction, and which is a very it's a tried and true technique, and it's great for identifying crystal structures. But when you're working with a material that has inherently low symmetry, like we believe this new structure of graphite is, it just makes it difficult to identify because there are many peaks, many X-ray diffraction peaks, which is what you take in order to define your crystal structure. Also, graphite, which is just carbon. Carbon, if you remember your periodic table of elements, it's rather high up on the periodic table, which means it doesn't have a lot of electrons. And electrons, the more electrons an element has, the better the X-rays will diffract off of it, the better signal you'll get. And because it doesn't have a lot of electrons, the signal you get from X-ray diffraction on a low electron material, as well as the low symmetry, becomes even more difficult. Additionally, you have the problem that it's also very small grain size. I mentioned that it was nanocrystalline, the nanocrystalline phase that we're making, and this further degrades your signal. And so the signal of what you're trying to measure becomes very low, and so you have to collect for long periods of time. There's a fourth problem that made it difficult to identify this phase is that the kinetics. It takes a long time to actually form the material. It takes hours, days to go from a compressed state into a further compressed state, such that many groups have been looking at this. Like I said, it's been 50 years when this first had been identified.
It's been 50 years of a process which is just now coming into fruition.
That's right. But so there were a number of factors. But the actual compression part was not the issue. That's very easy and routine. It was the slow kinetics, the slow formation of the new phase, the small amount of electrons in carbon itself makes for low signal. The nanocrystallinity of the sample also makes for low signal, as well as the low symmetry of the structure. And so you had these four different things working against really any group being able to firmly confirm the new structure. And once we figured out that these were going to be issues, we just made sure that our measurements were going to be long enough, and we were patient enough to wait for the structure to really come to being and be in its stable form. But the theory that I mentioned, that there are many groups out there that had been trying to predict what the structure would be, and there have been no less than a dozen different structures that have been proposed in the last 5 or 6 years to see what this structure is. Unfortunately, all but one of them did not fit the data.
I find the structure and the mapping of this potentially interesting. Is there any reason that we should speculate that the ceiling should be at diamonds, that at some point we won't be able to figure out a structure which is much harder than the diamond currently?
No, if we can, the real test. So the way that we have said that this material that we formed is, has comparable hardness or comparable strength to diamond, is because in order to actually make the pressure, we use what's called diamond anvil cells. So we're using diamond itself to pressurize this graphite. And when we release the pressure off of the diamond anvils themselves are damaged. And so if you were just diamond and try to scratch it, just if you had anything just at your desk there and had a diamond and try to scratch it, the only thing that would scratch diamond itself is diamond, or something as hard as diamond. And so the fact that this material damaged the diamond suggests that it is as hard as diamond. If we wanted to find an actual number of what that hardness is, we would need to have the material at room conditions, and then they have a number of hardness tests that can be done. And this is done with any kind of material, where they actually try to indent the surface of the material. Unfortunately, we haven't been able to recover this structure to room conditions yet. So those kinds of measurements have not been made, although attempted, but have have not been successfully completed because we cannot retain this structure at ambient conditions as of yet.
Well, looking at something which is hard, but for the moment temporary. I'm Andrew Hiller for the Prism, and I've been joined by Kanane Lee, who is an assistant professor of geology and geophysics at Yale, talking about the creation of a substance as hard as diamonds. Thank you for the explanation and your time.
Thank you.
And now, a moment in the prism. The issue of diamonds and hardness brings to mind the question of perseverance. Many people think that the purpose of the prism is to find answers. It's not. This is a show about exploration, wandering, questioning. I delight in finding scientists who don't know the answers. Those are the ones I trust. Unlike the law, where the Supreme Court can settle an issue, nothing in science is ever settled. This show is about the quest, the journey, and the expansion of understanding. I hope you enjoy these trips through the prism and do find some answers. But also, think of many more questions. If you do, let me know. Comment at capitalcorrespondent.com. That's capitalcorrespondent.com. And thank you for listening. I'm Andrew Hiller. This time we look through the prism to find something that's suddenly gone missing. Astronomers are a bit befuddled at what's going on around a star they've dubbed TYC 82412652. Recently, the star was thought of as a young analog of our own sun, and one that displayed all the characteristics of hosting a solar system in the making, before it transformed completely. Now, very little of the warm, dusty material that some scientists thought might originate from the collisions of the rocky planets are still apparent. What happened to the dust is a bit of a mystery, and donning the tweed coat and a magnifying glass is UCLA professor of astronomy, Benjamin Zuckerman, who's here to deduce what happened. Welcome, Dr. Zuckerman.
Thank you. Nice to be here.
Thank you. Well, first, can you tell us a little bit about this? Where is it? What does it look like? How close is it?
It's about 400 to 500 light years from the Earth, and since a light year is trillions of miles, it's a long way away in terms of how we normally think about things here on Earth. But astronomically speaking, it's actually very much in the neighborhood, the local neighborhood, and is one of the closer objects to the sun. It's a young. The star of interest is a young star, about 10 million years or so of age. Now, again, 10 million years might not sound very young to most people, but when you contrast it with the 4.5 billion years our sun and Earth are, 10 million years is actually quite young.
So for this neighbor, we've been sort of peeking through the window and watching it since at least 1983. And we've been noticing that there's a lot of dust and a lot of material that was circulating around the star. And then what happened?
Well, it's beginning in 1983, which was the first time that this star had ever been observed at infrared wavelengths. The star was putting out huge amounts of infrared radiation. The way most people would be best familiar with infrared radiation is thinking in terms of heat. When your stove is on and it feels warm, or when you feel your warmth coming out of an object that's radiating, like your radiator, that's infrared radiation, and that's the kind of radiation that the telescope, actually Space Observatory, was sensitive to back in 1983. And detected from this star very, very strong infrared signal. And then over the course of the next 25 years, a second satellite above the Earth's atmosphere detected the same, a very similar amount of infrared radiation, and the team of astronomers I work with studied this star from a ground-based telescope in Chile one of the largest telescopes on Earth, and we also found the star to be very bright at infrared or heat wavelengths. And that was up until about 2 or 3 years ago, and then to everyone's surprise who was studying this star, over the course of only a year and a half or so, between sometime in 2008 to early 2010, so at most a year and a half, this strong infrared signal just essentially totally disappeared, and nothing like this has ever been seen previously by astronomers to happen around a star.
Do we have any idea what that reduction of infrared signal could possibly indicate?
The signal itself, the infrared signal that used to be there but isn't anymore, is due to little trillions, gazillions of little dust particles that orbit around this, or that did orbit around this star. What happens is the light from the star comes out, hits the dust particles, is absorbed by the dust particles, and re-radiated as heat or infrared energy. That's essentially exactly what's happening when the Earth intercepts sunlight. The Earth absorbs that sunlight and then re-radiates as infrared radiation. And actually that has to do with climate change and global warming and all those kind of things, because this infrared radiation that the Earth is emitting isn't getting out as effectively now as it did, say, 100 or 200 years ago. At any rate, so an object, whether it be a planet or a dust grain, absorbs the starlight and re-radiates it at infrared wavelengths. And so what's happened is somehow these gazillion, trillions of dust particles that were previously orbiting around this star have disappeared in some totally mysterious way that neither my colleagues and I nor any of the people who have learned of our discovery have yet been able to explain in any convincing way. I mean, we and others have thrown out various possible or conceivable explanations, but none of them are anything like convincing at this point.
Well, let me throw out a possibly dumb question. New stars coming out, it's generating a lot of energy, it's beginning to manifest more and more gravity. Could it be sucking in all this dust?
Well, we think that the dust was there initially orbiting around the star. In particular, it was orbiting, if you imagine the Sun-Earth system, it was orbiting the dust was orbiting around the star initially at a distance about half the distance between our sun and the Earth, more or less where the planet Mercury orbits around our sun. So it was orbiting at something like half the distance between the sun and the Earth for at least decades, and maybe a long time before that. And then, since it's disappeared, there are only a few possibilities. One possibility is it's somehow been accreted onto the star, so it's fallen onto the star. Another possibility is that somehow something's come along and blown the dust away from the star. And I suppose there are other possibilities, too. Maybe the dust all got together really quickly and formed a moon or a planet or something. But a year and a half seems pretty incredibly fast for something like that to happen. So we think most likely, but again, nobody really knows for sure, that either the dust was accreted somehow onto the star for some reason, that the star gobbled up all this dust, and it was a huge amount of dust, or somehow maybe the star put out a big burst of energy and blew the dust away from the star. But there's no evidence that this star does. There are some stars that do occasionally put out big bursts of energy, but there's absolutely no evidence at all that this star is one of those.
Now, on the Prism, we are covering a story about one of the stars that Kepler has discovered, and two planets which are circling, apparently, this star. I think it's Kepler 36. And one of the astronomers told me that the way they found the star is they found this planet, is that the planet would, for just a very small period of time, obscure a little bit of the light that was emanating from the star. Have you guys been looking to see if there's something new blocking the star rather than just the loss of this infrared field?
Yeah. Well, in principle, Andrew, that's another way to account for the disappearance of this infrared signal, and that is if somehow a screen was put between the Earth and this star and the warm dust orbiting around it, then the dust in principle could still be there, but just something's blocking our view of it. And we seriously considered that as a possibility, and in the paper that we published in the magazine, the journal Nature, we discussed the possibility that maybe the dust really is there and our view of it is just being blocked. But based on various measurements that we made or that satellites made that we show and discuss in our paper, we feel we can very convincingly rule out the possibility that this dust is just hidden from our view by some opaque screen between us and the warm dust. The dust has a temperature of about 400, or had it when the dust was there, at a temperature about 450 degrees or so, where the Earth's temperature, this is absolute temperature, the Earth's temperature is about 300 degrees absolute, so it's somewhat warmer than the Earth is. If you put a screen of really cold dust, say 100 degrees or something like that, between the Earth and the warm dust, and that would block the radiation from the warm dust from reaching our telescopes at the Earth. But we were able to search for the presence of cold dust, for example, and there's absolutely no evidence for its existence. So we can pretty certainly rule out the possibility that we're just not seeing the dust and it's really still there. That just doesn't seem to be what's going on.
Well, and of course, the first rule of science isn't necessarily to find the answers, but is to rule out the things which can't be.
Yeah, that's a good point. When we first submitted our paper to Nature, what happens when papers get submitted to scientific journals is the editor sends the paper out to one or more referees, and who then, that is our peers in this case in astronomy, who then evaluate the paper, give their opinion, and tell the editor whether they think the paper should be published or not. And in the case of our paper, when we first submitted it, the editor at Nature sent it out to 3 different referees, and at least one and maybe 2 of them weren't very happy with the paper because they said, well, okay, but the authors should be able to explain this phenomena that they're reporting, and we were not able to explain the phenomena, but we eventually convinced the editor and the referees that this thing is that what we found is so mysterious and so strange and be of interest to so many astronomers and maybe even to people who aren't astronomers, that the magazine, the journal Nature, ought to publish the result anyway, even though we don't have a good explanation for what we're seeing. And eventually the editor and the referees all came around to our point of view, and the paper was published on July 5th.